Okay, I want to welcome everyone to today's sustainability seminar. My name is Nancy Holm. For those who haven't been here before, I'm the sponsored research coordinator here and also the seminar organizer. I'm pleased that everyone could come to ISTC this morning to hear our talk by Dr. Jean Bogner. I'm going to have her be introduced by Dr. Chris Storr, who's with the Illinois State Geological Survey. A few things I wanted to say before we get started is there's a sign-up sheet here. It was for our biochar meeting. I have one for our seminar. If you could sign that before you leave, then so we can keep track of attendance. Those who were here at the biochar meeting, I have your names down already. That's fine. And then I also have information on future seminars. This week we have one on November 10th, and then we also have one next week on November 15th, if you're available to come to see those. Also, all of our seminars are videotaped and will be archived on our website. So if you ever want to see any from the past that we've had for the last 3.5 years, those are available on the ISTC website. And then these upcoming ones usually are posted a few days after the event. So with that, I'll introduce Dr. Chris Storr.
Thank you, Nancy. It's a genuine pleasure and a privilege to introduce a friend and colleague, Dr. Jean Bogner. She's a research professor at the Department of Earth and Environmental Sciences at the University of Illinois at Chicago. She's a president of her own company, president of Landfills Plus Incorporated in Wheaton, Illinois. She has more than 35 years of experience in field and laboratory research related to landfill gas generation, emissions, migration, and recovery. She was a real pioneer in this field, by the way. She was the leading coordinator. She was the coordinating lead author for the chapter on waste management for the 2007 Intergovernmental Panel on Climate Change. Fourth Assessment Report, Working Group Number 3, Mitigation. As you might remember, this was the group that was awarded the 2007 Nobel Peace Prize. She formerly worked at Argonne National Laboratory for more than 20 years. She also worked here at the Illinois State Geological Survey. That's right, with John Kempton. Yep. And she's...
And a lot of names we all remember, Chris.
And if you ask her, she could probably tell you a lot about some of the Lamont Drift up in the Chicago area. In addition, she works extensively with the United States and international landfill gas recovery and utilization projects, including clean development mechanism projects in developing countries. So we're very pleased to have with us Dr. Jean Bogner to talk about landfill methane, emissions and oxidation. Jean?
Okay. No, I don't need that. Thank you, Chris, for that nice introduction. Those of you that have been here for the biochar meeting, I'm very tempted to start out by saying, and now for something completely different. But there are a few overlaps. My co-author is Kurt Spokus, and Kurt and I have actually worked together more than 20 years with respect to landfill methane emissions and oxidation research projects. And I've also worked a bit with Krishna Reddy at my institution at UIC with respect to his evolving work on looking at biochar amended landfill cover soils. So we have some interfaces here. But what I'd like to do today, and can everybody in the back hear me? Because I'm only being mic'd, I understand, for recording. I'm not being mic'd with respect to amplification in this room. So if you can't hear me in the back, please just raise your hand and I will speak louder. I'd like to talk today about landfill methane emissions and oxidation. And what I'd like to do is give a little bit of background on landfill gas and landfill methane. This is familiar to a lot of you, so you may be hearing something you already know about. Talk a bit about methane as a greenhouse gas, and then bring it back to the landfill environment, talking about landfill methane emissions measurement and modeling and quantification of landfill methane emissions at various scales, including working with the global estimates and then particularly stressing some work that Kurt and I have been involved in the last 4 years with respect to measuring and modeling emissions at 2 sites in California. How do we make methane in a landfill? We put in garbage, which basically consists of a number of complex polymers, cellulose, other polysaccharides, proteins, and a number of trophic groups of bacteria, hydrolytic bacteria, let's see if I got it, yeah, fermentative bacteria, acidogenic bacteria, acetogenic bacteria, through various intermediates, eventually produce products such as hydrogen, carbon dioxide, acetate, and mainly through the actions of 2 pathways for biogenic methane production, one of them being the cleavage of acetate into a molecule of methane and a molecule of CO2, and secondly, the reduction of CO2 with hydrogen. We produce biogenic methane in landfills. What happens in landfills is exactly the same as what happens in other anaerobic environments, soils, and sediments where methane is being produced biogenically. There are also a couple of pathways for methane oxidation. The major one in landfills is in cover soils, a group of microorganisms called the methanotropes can aerobically oxidize methane to CO2 and water vapor, almost identical to combustion reaction, but accomplished at near Earth's surface temperatures by microorganisms. In anaerobic environments, there's also the possibility of anaerobic methane oxidation, primarily by sulfate reducers, possibly also by archaea. And this is a pathway which occurs through sulfate. So sulfate is required for anaerobic methane oxidation. This becomes more important in landfills which have accepted large amounts of things like construction and demolition debris, which includes gypsum wallboard, so there is some sulfate present. Generally, in landfill settings, the most important pathway is the aerobic pathway in landfill cover soils, where oxygen is derived from atmospheric oxygen. But in cases where there's high sulfate in landfills in the anaerobic zone, this pathway is also possible. And in fact, there's some literature which indicates that sometimes in leachate collection systems we see carbonate crusts, which are probably derived from this particular mechanism. What's in landfill gas? Besides methane and carbon dioxide, there are a lot of other things. There are minor components. If we collect gas in an engineered gas extraction system, we can see oxygen and nitrogen from air that's pulled into that extraction system. We can also see hydrogen sometimes as an intermediate. You remember from the pathway that I showed you in the first slide. Hydrogen is an intermediate that can be measured in young landfill gas. It can also be measured in hot landfills where temperatures are so high that the methanogenesis is suppressed and we see a buildup of hydrogen rather than that hydrogen being turned over very quickly to methane. We also see hydrogen sometimes from specialized waste in landfills. There are some abiotic reactions involving things like aluminum dross waste, which has been associated with elevated hydrogen in some landfill gas. And then we get to the trace components. And as you can expect in landfill gas, there's probably something more than 200 trace components present. You see the volatilization of all of the things that people have historically put into landfills and under landfill conditions of 25 to 35 or 40 degrees C, what gets volatilized. We see hydrocarbons up to about C10. We see aromatics. We see reduced sulfur gases. We see chlorinated species. We see some volatile siloxanes from our underarm deodorants and personal care products. We see a lot of things that are just directly volatilized. We also get the degradation products of many abiotic and biotic reactions, particularly anaerobic biodegradation pathways in the anaerobic landfill environment. We see some generation, specialized generation of metalloids, for example, like trimethyl arsine occasionally occurs. So there's a lot of possibilities. But today I'm going to only really focus on methane. And this slide is an attempt to show a generic landfill cell. And then in the anaerobic zone, if we produce a molecule of methane, what are the possibilities for what can happen to that molecule of methane? And those possibilities include that methane can be captured by a gas extraction system. Usually these systems consist either of vertical wells, which are installed after landfill reaches final grade, or horizontal collectors, which are installed concurrent with landfilling, which permit earlier and more frequent recovery of landfill gas. Methane can be emitted to the atmosphere directly. Methane can be oxidized by methanotrophic bacteria in the aerobic zone, as Krishna was talking about earlier with respect to putting some biochar in that zone to perhaps speed up the oxidation process and absorb methane so it sticks around a little longer for oxidation to occur. Methane can migrate laterally, particularly at older unlined sites, given unsaturated and favorable geologic materials adjacent to that landfill. And methane can be temporarily stored internally within the landfill volume. So we can write a little mass balance equation here that the methane that's produced is the sum of the recovered, the emitted, the oxidized, the migrated methane, and the change in methane storage. So we're focusing on methane. And let me jump from landfill methane particularly to look at atmospheric methane in the next few slides. And these are all from the IPCC fourth assessment report from the Working Group 1 report, which is all available at the website www.ipcc.ch, CH for Switzerland. But these are what have become known as the hockey stick curves because of their shape. And what we have here is time before present, and basically going back to the year 10,000. And we see curves for nitrous oxide at the bottom, methane in the middle, and carbon dioxide at the top. These are the three most important well-mixed greenhouse gases in the atmosphere. Obviously, there are many things that contribute to warming and cooling of the atmosphere, but in terms of warming the atmosphere, or as the climatologists call it, positive climate forcing, the well-mixed greenhouse gases have been documented to have a strong signal with relatively small error bars, at least over the last 10,000 years. The more recent data here are from actual atmospheric observations, and then it's very nice to use data from ice cores and the gaseous inclusions in those ice cores to infer what atmospheric concentrations were in the near geologic past. So we have changes in atmospheric concentrations as shown here, and then on the right-hand side, those changes in concentrations have been converted to positive radiating forcing in terms of watts per square meter. These are the same units that we use to measure solar radiation. And you can see that the most radiating forcing here is attributable to CO2. Methane becomes the second most important greenhouse gas, and nitrous oxide becomes the third most important greenhouse gases. And just for reference here, I've indicated the atmospheric concentrations now for the three greenhouse gases, and also concentrations at about 1750, which is considered pre-industrial time. So you can see the relative increases that have occurred. A little bit about the three different greenhouse gases. Carbon dioxide, the most important one, is mostly derived from fossil fuel combustion. Both mobile sources and stationary sources, our cars, our power plants, our industries. Methane, the second most important greenhouse gas, has many, many sources. A number of these sources are rather poorly quantified and not tremendously understood. Methane concentrations in the atmosphere have actually wobbled about a bit in the last 2 decades, and some of that wobbliness is not very well understood, quite frankly. But among the sources of methane to the atmosphere, about 30% is natural, from natural wetlands, and the rest of the 500 or 600 teragrams per year of methane is derived from leakages from natural gas, leakages from coal beds, rice production, biomass burning, ruminant animals, and landfills. So there's a lot of sources of methane. The third most important greenhouse gas is nitrous oxide, and the major source of nitrous oxide is really fertilized soils. It represents a loss of nitrogen to soil systems. Generally, when we're talking about greenhouse gas emissions, the actual mass or emissions of the various greenhouse gases are converted to their carbon dioxide equivalents. And basically this unit represents a multiplication of the actual mass of a given greenhouse gas, such as methane, by the global warming potential for that particular gas. Now, global warming potential, by definition, carbon dioxide is 1, and global warming potentials can be defined on various time frames. By convention, the most common one that's used is the 100-year global warming potential. And basically, for a given gas, this represents the mixing of a given greenhouse gas in the atmosphere, and it also represents the infrared absorption of that greenhouse gas, and in particular the infrared bands where that absorption occurs. So global warming potential actually changes with time based on the mix of different greenhouse gases in the atmosphere. And I've just listed a few of them for methane here. The 100-year global warming potentials for methane have changed from the IPCC second report to the third assessment report to the fourth assessment report, from 21 to about 25. So what this says is that a molecule of methane basically has something more than 20 times the global warming potential of a molecule of CO2. That's what we're talking about here. And from the IPCC fourth assessment report, I think it's interesting to compare the distribution of emissions between different sectors. And what I've done here is taken the numbers from, this is from the IPCC fourth assessment report for Working Group 3, and there are 2 sets of bars for every sector here. The first bar is the 1990 greenhouse gas emissions, and the second bar is the 2004-2005 greenhouse gas emissions. But something to note is that these have all been converted to carbon dioxide equivalents based on their global warming potential. So these are normalized emissions based on carbon dioxide equivalents. Our units here are gigatons, CO2 equivalents, so 10 to the 9th tons per year. And also the bars have been colored with respect to what portion of the emissions are CO2 in red, methane in green, nitrous oxide in blue, and then also the small contribution from high global warming potential fluorinated gases, such as the CFCs and some other gases that have been previously subject to limitations under the Montreal Protocol. So the global warming potential of carbon dioxide is 1. We've gone back here to the global warming potential from the IPCC second assessment report, which is 21. not 25 from the fourth assessment report. The reason for this is that 2021, the numbers from the second assessment report are used for Kyoto compliance for countries which are subject to the Kyoto Protocol. And then the global warming potential for nitrous oxide, as reflected here in the normalized numbers, is 310. So if we go across, we have the emissions from energy supply, we have emissions from transport, we have emissions from residential and commercial buildings, we have emissions from industry, from agriculture, from what's land use change in forestry, and from waste and wastewater. I think you'll see right away there's a lot of red here. So 77% of the 2004-2005 emissions are attributable to carbon dioxide, roughly 14% from methane, and 8% from nitrous oxide, and then a small 1% from the fluorinated gases. If we look at the different sectors in comparison to each other, the waste and wastewater emissions are actually the smallest of the characterized sectors here. The largest ones, the large CO2 emissions from energy, transport, and industry are shown as well. Most of the forestry land use change, this is a large reflection of biomass burning here. And agriculture, like waste and wastewater, is also a sector with high methane and high nitrous oxide emissions. So these are things like manured fields and nitrous oxide, already talked about as being an inefficient and use of nitrogen and loss of nitrogen from the soil plant system. If you, I think that's all I want to say about that one. What can we do to mitigate greenhouse gas emissions? These are also some bar graphs from the IPCC fourth assessment report. If we added up all of the bars in the previous one from 2004 to 2005, and I can just go back here, the total is approximately 49 gigatons CO2 equivalent, which represents a very large 70% increase since 1970. And of that 49 gigatons or so, we'd need to add up the bars here, which show mitigation potential, again, across these different sectors, with respect to different economic levels. So these are an economic mitigation potential at various price levels. The first bar in each case is mitigation potential at less than $20 per ton CO2 equivalent. The second is less than $50, and the third is less than $100. These are cumulative, so in all cases, the right-hand bar is going to be the highest. And if we added up the right-hand bars in each case, you can see that we're still not quite at, given current technologies and current economics, that 49 gigaton CO2 equivalent. But the point being here is that all sectors and all regions have the potential to contribute to mitigation. You can see that these bars are also divided into different regions, developing countries, which have quite a large potential for mitigation, even at low price levels, economies in transition, which is mostly the countries of the former Soviet Union, the OECD countries, which stands for Organization of Economic Cooperation and Development, the more highly developed countries, and then the world total. In this set of graphs, transport is not divided according to regions because it includes international air transport, which you really can't assign to any particular country. Focusing specifically on the waste sector, and I'm going to run through the numbers as reported in the IPCC fourth assessment report, and then talk a little bit about where those numbers have come from. Actually, the waste sector in total has the about 1.3 gigatons CO2 equivalent. These have been converted to million ton CO2 equivalent, so we've lost 3 orders of magnitude here from the previous graphs. Please keep that in mind. The landfill methane part of that is roughly 50% here at around 600 million tons CO2 equivalent. Wastewater methane is most of the rest, which represents anaerobic conditions associated with wastewater systems and then loss of that methane. A little bit from wastewater nitrous oxide, and a small amount from the incineration of waste due to carbon dioxide that's produced from fossil carbon, which is part of the waste mass. So this would be CO2 from carbon in waste which has been incinerated, where the original waste materials are things like plastics or synthetic textiles, which represent fossil carbon as opposed to biomass carbon. There are a number of ways to develop these numbers. I'll talk about that in a minute, but if you just sort of keep in mind their overall magnitude. And I've also added in yellow here, the EPA, just this current year, has put out a new draft report on global non-CO2 greenhouse gas emissions. And these numbers haven't really changed too much. These are the numbers as they reported for 2005, and then some projections for 2030, which are fairly similar to the ones for 2020 from the IPCC Fourth Assessment Report.
Pardon me, what were the numbers just recently released, just this past week? And I'm sorry, I can't be more specific, but it was noted total greenhouse gas release. The numbers were much higher than even the highest.
I think you're talking mostly about the CO2 numbers as opposed to the methane numbers here.
Okay.
And I don't have that number on top of my head today, but yeah.
This was
Just recently, yeah. Yeah.
this week.
Yeah. So where do these numbers come from? And what I'd like to do is compare and contrast a little bit between the global estimates. And again, I'm going to specifically talk about landfill methane emissions and how numbers are developed on a site-specific basis with respect to what those emissions are on a much smaller spatial and temporal scale. And I think I should probably preface this discussion in that the numbers from the global numbers from a lot of the different sources, not only landfill methane, but particularly the methane emissions from other sources, to some extent the nitrous oxide sources, and to some extent the CO2 sources from various small categories, are actually rather soft, is probably the best way to say it. And for landfill methane, particularly, these are based on annual inventory reports, which are made to the United Nations Framework Convention on Climate Change by developed countries, which are used IPCC national greenhouse gas inventory methodologies. And then those annual reports are combined with estimates for a given year for developing countries, which are not required to report annually to the UNFCCC. So basically, the global totals need to depend on when somebody decides to put this all together. And the estimated emissions are based on a first-order kinetic model, which is derived from anaerobic digesters, where you put in a given amount of waste on an annual basis, and you model the methane generation from that given amount of waste based on a methane production potential and a kinetic coefficient, which describes how fast the methane is being produced relative to the total potential. And then you combine the methane that is estimated to be produced in 1 year with the methane from waste disposed of in that year, and you combine it with the methane from the waste disposed of in previous years. So what's required to do that is the amount of waste that's produced in a given country in a given year, how much of that waste is landfilled, and what's the composition of that waste relative to your model parameters that are applied to this estimation. And in the U.S., we also do something similar. It's interesting in the U.S. that landfill methane emissions are not regulated directly, but under the Clean Air Act, we regulate the emissions of non-methane organic compounds. But that regulatory procedure uses a similar gas generation model to estimate what those emissions are. And then compliance consists of installing a gas collection and control system to mitigate the emissions of those NMOCs. With respect to going to a specific landfill and measuring emissions of methane, there are lots of choices. We can use static closed chamber techniques. We can put a box over the surface of the landfill. We can do a time series of methane concentration measurements in that box. And we can use the volume over the area covered by the box times the change in methane concentration over time within that box as a direct measure of methane emissions in terms of a mass per area per time. So units like grams per meter squared per day. We can use a variety of above ground techniques at a slightly larger scale. You can appreciate that these boxes are oftentimes on the scale of a square meter or at most a few square meters. Above ground techniques can consist of dynamic plume tracer measurements where we emit a tracer and then downwind we measure the concentrations of that tracer and of methane. There are micrometeorological methods which measure the dynamic transport, the turbulent transport of gases near the ground surface to the atmosphere. And we can use below ground techniques. For example, we can look at concentration gradients and use a diffusive flux calculation, some form of fixed law. We can look at pressure gradients to measure emissions of methane to the atmosphere in various landfill settings. So in one case, at the larger scale, these estimates are very highly simplified based on models and based on assumptions. And then at the site-specific level, these emissions measurements can get very specific. But as you might expect, because I've listed so many techniques, there is no one perfect technique. So in many cases, 2 or more techniques are used in parallel to better characterize the emission from specific landfill settings. I want to talk a little bit about the national methodologies, and this is basically what some of what I've said before. The references for the national reporting requirements is the 2006 IPCC National Inventory Guidelines. And basically the emissions consist of, as you see in the middle of this slide here, the modeled theoretical generation, as I described, based on a first-order kinetic equation, minus the measured recovery in a given country, minus the estimated oxidation. And to date, the estimated oxidation can only be 10% or 0, which goes back about 10 years to the first, from 2006, to the first paper in the literature which attempted to measure annual methane oxidation in landfills. And it happened to be measured at a very, very small landfill site in Nashua, New Hampshire. So the IPCC methodologies, both Tier 1 and Tier 2, relate to a theoretical methane generation model. The IPCC methodologies also allow a Tier 3, which is the use of a more complex field-validated methods, and I'll get to a possibility for a Tier 3 methodology a little further in this presentation. So what are some of the issues with this current methodology? There's high estimated uncertainties. IPCC themselves have estimated that the uncertainty is a minimum of 30% to more than twice. For many countries, the waste data itself is highly uncertain or, in fact, does not exist. So people have sometimes gone with the use of surrogates, such as gross domestic product or energy consumption or different measures of consumption on a per capita basis, because waste generation is related not only to population, but it's also related to prosperity. Something to consider is that the first order decay, the first order kinetic models were actually never field validated for emissions. They were only compared to methane recovery, which is related to their original use to forecast the amount of gas that might be collected by a commercial gas extraction system. I will talk quite a lot about methane oxidation. 10% is certainly not representative. And the current methodologies, as you might have already figured out, give no consideration to the effect of cover materials on top of the landfill to reduce and retard emissions or for methane oxidation to happen in those cover materials. And more and more, where site-specific emissions have actually been monitored, the kinetic models yield really highly inaccurate results in one-to-one comparisons with field data. And I'm just going to give a couple of examples. I'm going to talk quite a bit today about methane emissions at 2 California sites. And we actually applied the Tier 1 IPCC model to modeling methane generation in those sites. We assume 75% recovery, which is the US EPA default. You can see the curves here for generation. The red curve is the Shoal Canyon site in Southern California, Los Angeles area. The blue line is the Marina landfill in Northern California. The squares are 75% of those numbers for roughly the year 2010. And I will tell you that the current gas recovery at those sites is about 2 to 3 times the measured recovery. So it doesn't work at all. And this is more and more the case as during the last decade or so we've done more field measurements of both emission and recovery and compared those data to the models. And this is a second example. Kurt and I were involved in a study in France which consisted of measuring the complete methane mass balance at 7 different field cells. And we modeled methane generation at these cells. And these were well-controlled field cells, so we had very, very good information on waste inputs. And what the x-axis in both cases here is modeled methane generation in kilograms per day. And then in the y-axis in this case is measured methane emissions from these same 7 cells. They all had gas extraction systems except this high value here. And first of all, note that the y-axis is on a log scale. There's really no correlation whatsoever between the modeled generation and the measured emissions. Whereas down here, which was the original purpose of these first-order kinetic models trying to model methane recovery, you can see there's actually quite a good correlation between the modeled methane generation on the x-axis and the measured methane recovery on the y-axis. So we need to do a little better. Now, over the last decade and a half or so, a lot of field and laboratory measurements have been done on methane emissions and methane oxidation in landfill settings. And we know by looking at that literature that there are 3 major factors which affect the methane emissions. Those factors are whether or not landfill gas recovery exists, because the installation of an engineered gas extraction system can extract a large percentage of the methane as it's being produced, and it will also tend to reduce the methane concentration in soil gas at the base of the cover materials, thus reducing the diffusive flux, because as you'll all remember, the driving force for diffusion is a concentration gradient. Also, the thickness and physical properties of the different cover materials. The daily, intermediate, and final cover materials at landfills are distinctively different in terms of their physical properties and their thickness. So they all have different emission signatures. And finally, closely related to that is the seasonal rate of methanotrophic oxidation in those cover materials, which can reduce emissions depending on the seasonal oxidation capacity versus the gross rate of methane flux from the anaerobic zone to the aerobic cover materials above. Try it again. There we go. Okay. So first, I'd like to talk about some studies that were done in Kurt's laboratory with respect to quantifying the dependence of methane oxidation rates on soil temperature and moisture. And these studies consisted of something over 2,000 laboratory incubations using cover soils from 2 California sites. And the first question we might ask is, what is the effect of temperature on relative rates of methane oxidation? Here we're looking at a full temperature range from about -5 degrees C up to 70 degrees C. And the plot here is, you can see on the y-axis we go from 0 to 1. This is a normalized plot which relates the rate at a specific temperature to the maximum rate for the corresponding soil moisture potential for each soil. These were done as small laboratory incubations with about 2.2 volume percent methane in the headspace, which was the average for the 10 centimeter depth at the various field sites. So you can see there's a very nice curve here with maximums at around 25 to 35 degrees C, and then dropping off very sharply at lower temperatures and at higher temperatures. So there's an optimum range for methane oxidation with respect to temperature. Now let's do something very similar for soil moisture. And these are also normalized curves which represent the rate at a given soil moisture potential divided by the maximum rate for the corresponding temperature of the incubation. And you can see by the numbers here, we have plots for, in the left-hand side, temperatures less than 5. In the middle, most of the temperatures in the range of 5 to 40, and then some others at the right hand here for temperatures greater than 40. And the x-axis here is soil moisture potential in kilopascals. And again, these are normalized curves, so the y-axis goes from 0 to 1. And you can see that particularly if we concentrate here in the middle in the middle graph, you can see that the optimum is approximately minus 33 kilopascals, which is pretty much at the water holding capacity. And the soil moisture potential for 50% of the oxidation capacity occurs at about minus 600 kilopascals. And the soil moisture potential threshold is down here at around minus 1,200 kilopascals. So this is a description of the effect of soil moisture on relative rates of methane oxidation, which we can add to the effect of soil temperature. And there's one more thing I want to talk about with respect to oxidation, and this is the effect of methane exposure time with respect to oxidation rates. And here we have 3 sets of numbers, and I'd like you to mostly concentrate on the blue numbers here and not quite all of the detail. But what we have here is a comparison for soils, the same California cover soils, which had no pre-incubation with methane and were incubated at their field moisture content, where there's an oxidation range of about 0.05 to something over 200 micrograms methane per grams per dry soil per day. In the middle, the same soils were pre-incubated for 60 days with methane exposure, And the oxidation range there was from about 0.1 to 385 micrograms methane per grams dry soil per day. And then finally, the last set of columns and rows here is where the soils were pre-incubated for 60 days with methane, and the moisture was also adjusted to the field capacity, or the optimum moisture at about minus 33 kilopascals. And if we compare the oxidation rates for these three groups, you can see that with both the pre-incubation and the adjustment of soil moisture to the field capacity, that the oxidation rates were all quite high, all from about 100 to 600 micrograms per gram dry soil per day, and they were all within the same order of magnitude. So we've lost this several orders of magnitude variability, and we've achieved high and quite consistent methane oxidation rates by these two mechanisms. What that said to us is that much of the incubation data that's in the literature to date, which did not involve a pre-incubation and which did not involve a soil moisture adjustment, in fact is probably underestimating the true capacity of oxidation for these soils and is giving an oxidation rate which represents other conditions. So we think we're getting close to a maximum rate with these effects. Now let's look at some field data. We're going to go to Northern California with respect to the Marina landfill. It's a coastal site near Monterey. The Shoal Canyon landfill is a very large canyon fill in the northern part of the Los Angeles area near Glendale. And we did some simple static chamber measurements on the different cover materials at these two landfill sites. And then I'll show you some differences for methane emissions from those different types of cover materials. The final cover is shown in the rectangles and squares here. We measured these at several field campaigns over a 2-year period. So these locations changed with time as the landfilling operations changed. And so the rectangles and squares are the final cover. The largest area at these sites was the intermediate cover, which is represented by the circles, and then the daily cover was represented by the stars. At most landfill sites today, because they're large sites maintained over decades, the intermediate cover is the largest area because there'll be a series of cells, and then there'll be another series of cells overlapping that. And final cover is not placed on a landfill typically until it reaches final grade. A little bit on the climatic differences between the two sites. We're in California, so the climate is primarily Mediterranean. Precipitation falls during the winter months, but there were some differences between these two sites. We were trying to choose sites, contrasting sites in California with respect to climatic differences. The Shoal Canyon site is much drier and quite a bit hotter than the Marina coastal site, which is the wetter of the two sites. And in all cases, the March tends to be the wettest month at the end of the winter rainy season, and August tends to be the hottest, driest month at the end of the summer dry season. So we geared our field campaigns for March and August of 2007 and 2008 to capture in March, the wet extremes, the cool wet extremes, and in August, the hot dry extremes for these two sites. As I mentioned, we used simple static chamber measurements. We did the 4 field campaigns. We also quantified methane oxidation using the stable carbon isotopes of the methane that's being emitted in the chamber or the methane that's being captured in soil gas probes, and compared the del C13, the fractionation of the C12 and C13 in those samples, to the same fractionation in the deep landfill gas, the anaerobic landfill gas. Because methanotrophic microorganisms, according to temperature and some other dependencies, will prefer the C12 over the C13. So there's a fractionation that occurs with methane oxidation, and we can exploit that fractionation to get a quantification of the percent methane oxidation as the methane is emitted through soil cover materials. We also did some additional supporting data, as shown here, to make sure our techniques were working properly. Contrasting cover soils also a little bit for these two sites, and I've just listed them briefly here. In both cases, the daily cover materials consisted of sandy soils of about 25 to 30 centimeters. The intermediate cover at the marina site was roughly 50 centimeters, consisting of few wood chips over some sandy loam. The final cover soil at marina, you can see here the layering of the cover soil wood chips over sandy loam over clay. The Shoal Canyon soils were, for the intermediate and final cover soils, were typically very thick, highly compacted, locally derived sandy loam materials. And I've also indicated in the light blue here the soil gas methane at the base of the cover, because it needs to be pointed out that gas collection was very aggressively done at the Shoal Canyon site. So you can see that the soil gas methane at the base of the cover was, in the case of the daily covers, about 10 ppm, in the intermediate cover about 2.4 ppm, and in the final cover something about 35% methane. In contrast, the soil gas methane at the base of the cover at the marina cover soils was generally much higher, about 3,000 ppm on the daily, about 45% on the intermediate, and 55% on the final. I should note that like 90% of the waste in landfills in California, these sites are all subject to gas extraction over the entire landfill area. Now let's look at some of the emissions from these. There we go. These are average methane emissions from the Shoal Canyon and the marina site. And the top set of bars is the measured positive methane emissions using the static closed chamber method. And I've contrasted and composited the methane emissions, which represent the wet season dry campaigns, which are in blue, and the dry season field campaigns in red. And you can see the y-axis here is a log scale, so that overall the average emissions across these two different sites respectively for the three different types of cover materials at these sites vary over about 4 orders of magnitude. Our units here are all in grams per meter squared per day. The emissions from the Shoal Canyon site, which both had thicker final and intermediate cover materials and was much more aggressive with gas extraction, were typically lower. The daily cover emissions, as you can see here, for the marina site were around 10 grams per meter squared per day. They were quite a bit lower for the Shoal Canyon site, which again was much more aggressive with gas extraction. And I've also plotted the emissions here for the fresh refuse before daily cover, because these cells were all overlying existing refuse, so there were both methane emissions from the underlying refuse and also methane emissions from early methane emissions from the recently placed daily cover of previous days. Now, the other set of graphs here plots negative emissions, because in the static chamber you can measure an increase in methane in your chamber, but in the cases where the methanotrophs in the cover soil are able to oxidize all of the methane that's coming from the landfill sources, and additionally oxidize methane out of the atmosphere above the landfill, you can measure a steady decrease in methane concentrations in your static chamber. And so the possibility is that you can also have negative methane emissions or uptake of atmospheric methane at the top of a landfill. And everyone that's used static chamber techniques in landfill settings has seen some modest or larger number of negative methane emissions as well. And I've just shown here they generally vary within about the same order of magnitude from about minus 0.01 to about minus 0.04 in terms of average numbers. And we can compare those with the average methane uptake rate, for example, in what might be a comparable natural ecosystem from a 3-year study of California grasslands. And you can see that those uptake rates were actually a couple of orders of magnitude less. So in the great scheme of things, it's interesting to note that landfill methane emissions can be extremely high, as shown here for the marina intermediate cover material. We're pushing somewhere between 10 and 100 grams per meter squared per day on the average basis. But they can also be, we can also measure fairly significant rates of methane uptake in landfill cover soils. And in fact, they're the highest rates that have been reported in the literature from any soil environment. Maybe I can just, there we go, okay. Methane oxidation using the isotopic method here. I've just summarized the ranges of methane oxidation. And keep in mind that for the IPCC national methodologies, all that's allowed is 10%. But the numbers here are much more consistent with some summaries in the literature that generally indicate 30 to 50% or more methane oxidation is readily achievable in landfill cover soils. And I've just compared the measurements here using the isotopic method from chambers in the first set, here the first 2 lines, and then in the second 2 lines from using soil gas probes from both the marina and shoal final cover soils, and comparing the Del C13 from those chambers or from those probes with the Del C13 for methane in the anaerobic zone as collected from the landfill gas extraction system. So our numbers here generally range from about 30 to 50% over all of the samples for this particular field project. And finally, Kurt and I have collaborated now for about 4 years on 2 projects which consist of developing and field validating an improved landfill methane inventory model for California. And rather than rely on a methane generation equation here, we have relied on a model which encompasses the diffusive flux of methane through the cover materials and methane oxidation in those cover materials to arrive at an annual measure of site-specific and cover-specific landfill methane emissions, which represent the effect of the gas extraction system in reducing the methane concentration gradient and also the effects of the soil cover materials with respect to reducing emissions and promoting methane oxidation over a typical annual cycle. So we did one project for the California Energy Commission, which consisted of development and field validation of this model. And the Marina and Shoal Canyon data, which I just showed you, was used for the independent field validation of the modeling. The laboratory incubations were used to scale methane oxidation relative to seasonal changes in temperature and moisture, and I'll show you how that worked in a minute. And we're currently involved in a project to field validate the same model internationally, which is being funded by the Environmental Research and Education Foundation. And we're working collaboratively with a lot of field research groups in this country and overseas who are doing their own independent measurements of methane emissions and oxidation. There we go. Okay, let's get back here. There we go. The CalMIM model, developed for California. So CalMIM stands for California Landfill Methane Inventory Model. Consists basically of 4 parts. Sites are located according to their latitude and longitude. A simple input screen is used to indicate what the properties of the cover materials are and whether gas extraction exists. The second part ties in some very nice models that Kurtz developed independently for USDA, which for any point in the globe, these are globally validated models, primarily based on 30-year data, can give you a temperature cycle, a precipitation cycle, and SolarCalc gives you a simulation of the surface energy balance over a typical annual cycle. And also then part 3 ties in another model which was developed by USDA under Kurt, which consists of STM2, which is a soil temperature and moisture model for any layered cover soil. And these 3 then are coupled to a simple one-dimensional diffusion model based on the methane concentration gradient and a net methane emission oxidation model where methane oxidation is scaled to the seasonal variability in temperature and moisture based on the results of all the laboratory incubations I showed you previously. So what you get is annual methane emissions for each site, which is based on the integrated time and depth calculations. And these are based on about a 1 inch or 2.5 centimeter depth and 10-minute time intervals over a typical annual cycle. Just a little bit about the methane diffusion modeling. Obviously, this is driven by the difference in methane concentration through the cover soil, but methane oxidation is also requires oxygen. So the bidirectional diffusion of oxygen through the cover materials is also important in order to calculate the net emissions inclusive of oxidation. And just a little example of an input screen. We think this is a pretty easy model to use. So you put in the different types of cover materials. You can rely on the defaults in the model with respect to concentration gradients, or you can put in your own. We ask about how much of a given cover area is accounted for by a particular cover type. We ask about how much has gas recovery. We ask about the organic carbon content of the cover materials, and not too much else. You can set up any layered cover soil using USDA categories or using alternate daily cover materials, as we've taken data from the literature for those. And what you get in terms of output, and I've just shown an example here for the Marina Intermediate cover material, you get, this is days of the year from 0 to 365. This is methane emissions in terms of grams per meter squared per day. And the top curve, the red curve, is modeled methane emissions without methane oxidation. The blue curve is modeled methane emissions with oxidation. And then the various dots here are the averages from the field validation study, particularly for the Marina Intermediate cover material. But what is nice about the model input is it tells you how much methane oxidation does for you on a daily basis over a typical annual cycle. And just for reference, I've plotted here some of the other CalMIM outputs. This is an annual temperature cycle. This is an annual moisture cycle. And you can see that in general, for Marina at least, during the middle part of the year, the net methane emissions were reduced under more fairly favorable conditions of both soil moisture and soil temperature. So in summary, let me say, here's some recent publications which are related to the data that I've presented for the 2 California cover sites. There's a paper that's just been accepted in JGR Biogeosciences on the model. is a paper in JEQ on the seasonal greenhouse gas emissions. We also looked at carbon dioxide and nitrous oxide emissions at these two sites, which I didn't have time to talk about today. And finally, the paper which looks at the limits and dynamics of methane oxidation in landfill cover soils. If you want to try this model yourself, if you have a landfill site, it's freely available at the USDA website using the links here. The easiest way is to go to ars.usda.gov, click on Products and Services, and then click on Software, and then click on CalMIM. We're doing some incremental improvements and modifications to the model as we go along, so we're now at version 4.3c. And just as a final comment, I think you must always question where the numbers come from. So at various scales, if you're at the global scale, you can develop estimates of generalized numbers. But when you work down to the site-specific scale to look at emissions directly and methane oxidation and various cover materials, it's quite a different world. And if you're working in between to develop regional estimates, your choice is to do you scale down the national models, or do you scale up and do you aggregate the results that you get from more site-specific models and field measurements. And so I think I'd have to say at best, estimation of greenhouse gas emissions from many sources is still an inexact science, but we're learning a lot more through time as additional field and laboratory research is completed. And with that, let me thank the sponsors for this work, the sites for this work, and all of the field and laboratory personnel and UIC students who have helped us out in the process. Thanks for your time. I think I've gone over. I was a little long-winded. I started a little late, but forgive me for that, and I'd be glad to take any questions. Thank you very much.
Are there a few questions? Yes.
Have you found that forest, let me just give an example, when Katrina hit, 4 million cords of wood were dropped on the forest floor in Mississippi. Do you find any type of concentration changes based on the rot of that material over a 5 or 6 year period, or that affects your modeling?
Are you talking about
methane production from that biomass rock?
Decomposing forest material left at the surface.
When you have that large of a volume over that big of an area.
Well, you have to remember that at the surface of the ground, most of that's going to be aerobic degradation. And aerobic degradation is mediated both by bacteria and by fungi. Now, in landfill settings, interestingly enough, most of the decomposition is anaerobic. So we have microorganisms, but we don't really have much fungal activity because most of those are aerobic. So I think the differences between those two settings, and I can't give you a number for how much that would be on an area basis, because I suspect that number is in the literature, but I don't have that number on top of my head right now. But aerobic decomposition is going to probably be faster on top of the ground surface than anaerobic decomposition in the landfill, because you have the added activity of those fungi. And on a little aside, what happens in landfills is the fungi are great lignin degraders. So you put lignin in a landfill, it basically stays there forever. It does not demonstrably degrade in the landfill setting. Whereas cellulose is partially degraded over time, and more readily degradable organics can be somewhat more fully degraded over time. So if you look at the carbon storage in landfill settings, it's generally about 50% or more of the carbon that you put in a landfill never gets turned over to methane and CO2 carbon as biogas as a final product. So there's carbon storage in landfills as well as some potential carbon storage in biochar. I think, it's always good to keep in mind the carbon balance numbers for these different settings. But the main contrast for forest materials at the surface and landfill materials buried beneath the surface is the difference between predominance of aerobic decomposition and anaerobic decomposition.
Thank you.
Okay, if there's no more questions, or people can come up and talk to Dr. Bogner after the seminar came out. We are having a tour of our lab facilities for anyone interested. If you want to be up front here, it'll take about 20 minutes or so to tour.